Welcome back to the Organic Chemistry playlist. In this episode, we have an NMR practice problem here. And in this problem, we are asked 4 different things, so be prepared here. They're kind of self-explanatory, but we'll say it out. How many different hydrogen signals would we expect on the HNMR spectra? I then want you to rank those hydrogens based on which ones are more down or deshielded and downfield than others. All right, and then we're going to look at the carbon NMR, which ones are, or how many different carbon NMR peaks will you get, and how do they relate to each other via their downshield or their deshielded effects and downfield relativity to each other. So let's just label all our hydrogens here. I'll do that in red. We have a hydrogen here, 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 and here. So we know that for these hydrogens, because they're all in different separate environments, like this one has a fluorine as its direct partner, this one has bromine, this one has chlorine, this one has iodine. We know that these environments are relatively different to each other. So these are going to give rise to four HNMR peaks. Or signals, I'll say. So from this, we're going to get 4 hydrogen NMR signals. Where would we expect them relative to each other? So if I'm looking at these relative to each other, I know that to be deshielded, you have to have very low electron density that's kind of helping you stay shielded from that magnetic field. However, with an atom like fluorine, for example, that is one of the most electronegative atoms, the most electronegative atom on the periodic table there. So it is pulling electron density away from this molecule, and subsequently this hydrogen feels very electropositive and not having that electron density to make it shielded. So this means that we need to follow a trend of increasing in our downshield, or I'll go this way actually. So if this is like the most deshielded and this one is the most shielded, it's going to follow an opposite trend to electronegativity, where or actually it would be going this way, where this is the most electronegative atom here and this is the less electronegative atom. Oh my goodness, my handwriting. Anyways, you get the point. So if you're more deshielded, you're more electronegative. The least electronegative atom here is iodine. It's the lowest in the group of the halogens. So we know that iodine is giving this hydrogen relative to the other hydrogens the most shielding. So that there will be, and we'll put the iodine hydrogen in quotes, right? So that's this one here. That hydrogen. We know bromine's next up, so we'll put bromine. So for that hydrogen. Next up is chlorine and then fluorine. So that's how we rank those hydrogens there, because right, this one is the most deshielded and will appear most upfield, or sorry, downfield. Right, more of a chemical shift, but something like iodine, not very electronegative in comparison to the other halogens. That causes this one to be the most upfield or most shielded. All right, so let me remove some of this here. The next question asks about carbon NMR. How many different carbon signals would we expect? It's kind of the same as the hydrogens here. We have a carbon here, a carbon here, a carbon here, a carbon here, and they're all in their own respective little environments relative to each other. One's bound to the fluorine, bromine, chlorine, and iodine respectively. So this will give rise to 4 carbon-13 NMR signals. And carbon NMR follows the same kind of pattern. The most deshielded ones are going to be the most downfield and have the most chemical shift. So it's going to follow the same trend where the most deshielded or the most upfield. So we'll draw the delta sign and we'll draw this least. Okay, so where does it fall on the spectra here? Well, we know that iodine is, again, not the most electronegative substituent on this cyclobutane. So that means that this carbon feels the most shielded and is therefore going to have the least of the four in a chemical shift on that spectra. So we'll put iodine. Remember, it's not iodine we're referring to, it's the carbon that it's bound to. Then it follows bromine, chlorine, and fluorine, the exact same as the hydrogen NMR portion of this video we talked about. So that's it for this episode. Hopefully that explanation made sense. Shielding can be a very confusing topic, but don't get too technical with it. Just know the basics of it and what it is, and it'll be fine. So thank you guys for watching.